In this video, I want to do some examples of calculating vector line integrals. The first question says, given the following vector field and oriented curve C, evaluate the integral of f dot t ds. And the first example is f equals negative yx on the semicircle r of t equals 4 cosine t 4 sine t for t between 0 and pi. Okay, well, before we do this problem, let's just make sure we understand what's going on. So you have some curve. In this example, the curve is given by the semicircle, which is given by this parametric equation. So hopefully you recognize this r of t, this a cosine t, a sine t, is a parameterization of the circle of radius a centered at the origin. But t only goes from 0 to pi. So what that looks like is, here's the x-axis, here's the y-axis. You have a circle of radius 4, but you only want the part that corresponds to t going from 0 to pi. And that's this part. So you have radius 4. When t is 0, you're at 4 comma 0, and then as t increases, you go counterclockwise in this direction, and when t is pi, you end up at negative 4, 0. So that's your curve C. And you have some vector field f. In this case, the vector field is negative yx. But the point is that you have, at each x comma y, you have some vector given by f, right? It's a function of x and y. So at 0 comma 4 here, your vector f is, well, x is 0 and y is 4, so your f is negative 4 comma 0. So you have something like this, right? The point is that you have, so that's your f at 0 comma 4. The point is that actually at each point in space, you have a different vector. You have all these vectors. I don't know what they look like. You have all these vectors. But what you're doing is you're integrating the tangential component of the vectors f along the curve C. So this f dot t, the t is the unit normal vector to the curve. Right. Your t is the unit normal vector to the curve, so you have a t vector, like at this point, your t vector is going to look like this. That's your t. And your f, I don't know, your f might look like this or something. And then what you're doing is you're taking the dot product of these two vectors, f dot t, that's a number. So you have this function. This f dot t is a function on the curve C. Because if you plug in this blue point here, you take the f, you take the t, and you take the dot product, you get a number. So at each point on the curve, you get a number, and then that number, that function that you get, that's the function that you're trying to compute the integral of. Okay, over the curve C. And one of the things that you learn is that when you have this, so this is really like a t hat because it's a unit vector. When you have something like this, when you have a parameterization of C, this ends up equaling, say, from t0 to t1, your starting t and your ending t. You have a parameterization of C. This integral is equal to the integral of f dot r prime of t dt. So this is an ordinary Calc 1 integral. You're integrating, from like 1 to 2 or something, and then you have this function, which is a function of t. So you write f in terms of t, you figure out r prime of t, you multiply, you take the dot product, these are dot products. Okay, just make it more bold to emphasize. And then this is the function of t. And then you calculate the integral. Okay. So you may want to review why these two are the same. It's not too hard to see why it's true, but there's some theory behind it. So anyway, what you have to do to calculate this integral is you find the parameterization of c. Well, in this case, they tell you what the parameterization is. It's this r of t. So what we're going to do is we're going to go ahead and calculate the f dot r prime of t. So first we have to get f in terms of t. Well, your f is negative y comma x, and your x of t is 4 cosine t. That's x of t. And your y of t is 4 sine t. That's what x and y are as you're traversing the curve. So in terms of t, right, when you're only caring about the f on the curve c, your negative y in terms of t is negative 4 sine t. And your x in terms of t, well, that's 4 cosine t. So f in terms of t is negative 4 sine t, 4 cosine t. Let's write that down. So f is negative 4 sine t, 4 cosine t. And now we take the dot product with r prime of t. So we have to calculate r prime of t first. That's easy. Negative 4 sine t, comma 4 cosine t. Wow, it's actually the same. So when you calculate f dot r prime of t, you are going to get negative 4 times negative 4 is 16, so you get 16, and then sine t times sine t is sine squared t, and you get 4 cosine t times 4 cosine t is 16 cosine squared t, and then it turns out that this simplifies. So in case you don't see right away, if you factor out the 16, you get in the parentheses sine squared t plus cosine squared t, and that's 1, right? So 16 times 1, which is 16. So that's your f dot r prime of t. And now we integrate that from your starting t to your ending t. Well, that's from 0 to pi. So the integral along c of f dot t is equal to the integral from 0 to pi of 16 dt, and that's just going to be 16 times pi. So that's the answer. Now normally, this example was a little too simple maybe, because normally your f dot r prime of t will not just be a constant. It'll actually have t's in it, right? So you might get like t squared or something, and then you have to integrate that from 0 to pi. Okay, let's do another example. So it's the same f, but on the parabola y equals x squared from 0, 0 to 2, 4. So what's the difference? You have the same f, but you have a different c, right? It's the part of the parabola y equals x squared from 0, 0 to 2, 4. Let's draw that. So y equals x squared looks like this. And it's from 0, 0 to 2, 4. Like that. So c is this part. It's not the entire parabola, it's just part of the parabola. It starts 0, 0 and ends at 2, 4. That's your c. And what we're calculating is the same thing. We're calculating this line integral, this vector line integral. And we have to do the same thing. We have to find the parameterization of c. In the previous example, you were told what r of t was. Here you have to come up with the r of t. So what's your r of t? You need the r of t to even get started on this problem. So to figure out the r of t, one thing that is good to know is that whenever you have a function y equals f of x, you can just use t comma f of t. So you can use r, in this case you can use r of t equals t comma t squared. Because if you plug in all the t's, if you imagine plugging in all the real numbers t into this function, you're going to get the entire parabola. Now you don't want the entire parabola, you just want this piece of the parabola. So you have to think about, okay, where do you want to make your t start and where do you want to make it end so that you only get this piece of the parabola and not the entire parabola. Well, what t will make you start at 0, 0? What t, when you plug in t, will give you 0, 0 into this? 0, right? So your t should start at 0, and then where should it end? You want the point 2 comma 4, and that's when t is 2. And in general, you know, you're starting, since your x is equal to t, right? Your x of t is just equal to t, it's just always going to go from your starting x to the ending x. So in this case, it went from 0 to 2. Well, now we can finish the problem, because let's identify our x of t and y of t. That's our x of t. That's our y of t. And now let's write f in terms of t. So our f was negative yx, and in terms of t, that's negative t squared comma t. Now we need the r prime of t. That's 1 comma 2t. Now we need the dot product, f dot r prime of t. Okay, you take the dot product of these two, you get negative t squared times 1 is negative t squared, and then plus t times 2t is 2t squared. Negative t squared plus 2t squared equals t squared. So the integral along c of f dot t ds is equal to the integral from what to what? Your starting and ending times are 0 and 2. So you integrate from 0 to 2, f dot r prime of t, we calculated that's t squared, and then dt. And this is an ordinary Calc 1 integral, so hopefully you know how to do this integral. The integral is t cubed over 3 from 0 to 2, and that's 1/3 times 2 squared minus 1/3 times 0, 1/3 times 2 cubed minus 1/3 times 0 cubed, that's 8 over 3. And by the way, let's just, so that's the answer to the problem. And let's just maybe say a few words about what this number represents. So you do the integral, you get 16 pi, what does that tell you? Well, so basically, I mean, roughly speaking, this f dot t, that's the tangential component of f along the curve. So if you get a positive number, then roughly speaking, that kind of says that more often than not, f is going along the curve c. If you get a negative number, a really negative number, then roughly speaking, what that's saying is that your f is going against the curve c. So for instance, if your c, and c is, you know, it's given a certain direction, right? So it's not just something like this, you actually say which way you're going. So let's say c is going like this. So let's say it starts, say here, and then kind of traverses like that. So that's your c. And let's say that your f was like this. Let's say that's your f. Well, what's going on is when you take the tangential component of the curve, oops, well, how did I do that? You take the tangential component of the curve, so you take a unit tangent vector to the curve, that's your t. If your f is going against the c, it's like pointing in the opposite direction as the curve, then when you take the dot product, f dot t, you get a negative number, right? And so you get a negative number for each point on the curve, and so when you do the integral, you get a negative answer. So it's hard to give a more kind of precise meaning of this integral, but that's essentially what it means. If you have a really, it kind of measures how along the curve the vector field f is. Okay. Okay, that's all I wanted to say about these examples.